Welcome to the deep dive. Today we're tackling a challenge from one of our listeners over at AI.Code.Cast.
Oh, cool.
Yeah, it's all about splitting up tasks, like in a super efficient way.
Okay.
Like imagine you've got this huge project,
Uh-huh.
and it's like an array of, all these different tasks.
Right.
And your goal is to divvy them up among your team.
Yeah.
So no one's totally swamped.
I can see where this is going.
It's a pretty common problem, right?
Absolutely. And it comes up all the time, not just in team projects, but in tons of computing tasks.
Oh, totally. We're talking task scheduling, resource allocation, like making sure all those processors are humming along smoothly.
Exactly. It's
Yeah.
about finding that sweet spot where everything's balanced.
So how do we actually tackle this? I mean, it sounds pretty tricky.
Well, there are a couple of super clever ways to do it.
But lay on me.
First up, we've got dynamic programming, which I know sounds a bit intimidating,
Yeah. Oh, yeah.
but we'll break it down.
Yeah, please.
And then, believe it or not, binary search can actually crack this too.
Really? Binary search? I thought that was just for, like, finding stuff in a sorted list.
Right. It's surprising, but super effective for this kind of problem too.
Okay, color me intrigued. So let's start with the problem itself.
Okay, so formally it's called the split array largest sum problem.
Catchy.
I know, right? But it's actually pretty intuitive. You've got this array of numbers, right? And each number represents the size or effort of a task.
Okay.
You want to split this array into k subarrays.
Okay.
And the goal is to find the split where the subarray with the largest sum,
Like the biggest chunk of work.
exactly, is as small as possible.
So we're trying to minimize the maximum.
You got it.
Okay, that makes sense.
Right.
So it's all about balance.
Yeah, exactly. Finding that fairest split.
So, where do we even begin with solving this thing?
Well, the most obvious way is brute force, right? Just try every possible combination.
Okay, so we could put all the tasks in one subarray, then try splitting after the first task, then the second, and so on.
Yeah, exactly. But here's the thing. As the array gets bigger, or the number of subarrays we want increases, the number of possible combinations explodes.
Oh, yeah. I can see that getting out of hand real quick.
It's like trying every single route to get somewhere.
Yeah. No thanks. Gotta be a better way.
There is, and that's where these clever algorithms come in.
Okay. I'm ready for the cleverness. What you got?
So, like I mentioned, two main approaches.
Okay.
Dynamic programming,
Uh-huh.
and surprisingly, binary search.
All right, let's dive into dynamic programming first. That sounds pretty intense.
It might sound scary, but the idea is actually pretty simple.
Okay, good.
It's all about breaking the problem down
Right.
into smaller, more manageable chunks,
Right.
and then using those solutions to build up to the big solution.
So it's like building a Lego set or something. Start with the small pieces and work your way up.
Perfect analogy. That's exactly it.
Awesome. But you also mentioned binary search, and that's for finding stuff in sorted lists, right?
Right, but the cool thing is we can tweak it
Okay.
to actually search for that minimum largest sum we were talking about.
So instead of searching for a position in the array, we're searching for, a value.
Exactly. We're searching for the smallest possible value of that largest subarray sum.
My brain's starting to hurt, but I'm with you.
It's a mind bender for sure, but it works.
Okay, so how does that actually play out?
Well, we know the minimum largest sum has to be somewhere between biggest single element in the array, right?
Okay. Yeah.
And the sum of all the elements.
Right, that makes sense.
So we use binary search to efficiently test values within that range.
Okay, I'm following.
And for each guess, we check if we can actually split the array into k or fewer subarrays without going over that sum.
So like a guessing game, but a smart one.
Exactly. And binary search helps us narrow down the possibilities super fast.
I'm starting to see the appeal here.
It's pretty neat. And we can do it all with this handy little helper function.
Oh, a helper function. Tell me more.
It's called minimum subarrays required. It basically tells us if a given sum is actually doable, like if we can split the array without exceeding that sum.
Okay, so it's like our feasibility checker.
Exactly. It keeps us on track.
I'm really liking how this is coming together.
Yeah, it's pretty cool how these different approaches can lead to the same solution.
So we've got dynamic programming with its building blocks
Yeah.
and binary search with its clever guessing game.
Yep. And both can crack this problem.
Awesome. But let's not get ahead of ourselves.
Right.
Let's break these down one by one.
Sounds good to me. Where do you want to start?
Well, let's stick with dynamic programming for now.
Okay. We can explore the two main ways to implement it.
Okay, I'm ready to dive deeper.
Perfect. Let's do it. So dynamic programming, right?
Wow.
Two main flavors.
Okay, you mentioned top-down and bottom-up.
Right. Imagine like solving a puzzle. Top down, you start with the big picture,
All right.
break it into smaller pieces, solve those first.
So kind of like working from the complex down to the simple.
Exactly.
Uh,
Bottom up's different.
Okay.
It's like you build the foundation first
Uh-huh.
and then layer on top of that.
So start simple and get more complex.
Yeah. You got it.
Gotcha. So both ways solve it, but they like approach it differently.
Exactly. Different paths, same destination.
Can we see like an example to really get this?
Absolutely. Let's stick with our pizza.
Okay, love pizza.
So say our pizza slices are like 1, 2, 3, 4, 5.
Okay, different size.
And we're splitting it among 3 people.
So K3.
You got it.
Right.
Now, top down first.
Right.
We try cutting after the first slice.
Okay, so one and then the rest.
Yeah, then after the second slice and so on.
So we keep making cuts, and then we got to figure out the best way to split what's left right.
Yeah, it's like a recursive thing.
Recursive, like it keeps calling itself.
Exactly. Breaks it down to we're left with like just one subarray.
Gotcha.
And the key is to remember the solutions from those smaller pieces.
So we don't keep recalculating the same thing over and over.
Right. That's memoization.
Memoization, that's our cheat sheet.
Exactly.
Okay, so top down. Got it.
Now, bottom up.
All right, building the pizza foundation.
We start with the simplest case.
Okay.
One subarray, that's just the sum of all the slices.
Makes sense.
Then we figure out for 2 subarrays, trying all the cuts, building on what we already know.
Okay, so we're using the previous result
Exactly.
to solve for the more complex cases.
You got it. Keep going until we hit K, or 3 subarrays in this case.
So it's like a step-by-step process.
Right. Like building a house, you can't start with the roof.
Got to have that foundation.
Exactly. And just like with house plans, there are multiple ways to get to the same house.
Okay, so different approaches, same result.
Right. Top down, bottom up, both get us the optimal split.
I'm starting to see the beauty of dynamic programming.
It's pretty neat, huh?
Yeah. It's all about, like you said, breaking it down, using what you've learned, no wasted effort.
Exactly. Efficient, elegant.
All right, so dynamic programming, feeling good about it.
Ready for some binary search magic.
Yeah, bring on the magic. Still a bit fuzzy on how that fits in.
Remember, we're not searching for where to cut the array.
Right.
We're looking for that minimum largest sum, the optimal value.
Okay, yeah.
Binary search helps us find that.
So remind me, how do we set up that search range again?
Okay, so the lowest possible value, our starting point,
Uh-huh.
that's got to be at least as big as the biggest slice in our array.
Makes sense. Can't go smaller than that.
Right. And the highest...
I mean, if we just used one subarray, right? Sum of all the elements.
You got it. Perfect.
So our range is set. Now, how do we, like, use binary search within that?
We pick a value right in the middle.
Okay.
Our mid value, our guess for the minimum largest sum.
Okay, so like a midpoint test.
Exactly. Then we use that helper function we talked about.
Minimum super is required, right?
You got it. We give it the array and our mid value.
Okay, and it tells us if we can split it up without going over that mid value.
Right. If we can, then our minimum largest sum could be even smaller.
So we got to keep searching.
Yeah, we adjust our range, focusing on the lower half.
Gotcha.
And if we can't split it within that mid value...
That our guess was too small.
Exactly. Got to go higher, so we focus on the upper half of the range.
And we keep doing this, like narrowing down
Till our low and high values meet.
And that's our answer.
Bingo!
Wow, that's pretty slick. Binary search, who knew?
It's a powerful tool and super efficient, especially with big arrays.
But you said dynamic programming has its own strengths too, right?
Definitely. Sometimes it's more intuitive, and that bottom-up approach can be really good for saving memory.
Okay, so it's like choosing the right tool for the job.
Exactly. Each algorithm has its sweet spot.
This is amazing. We've come a long way from brute force.
Right. From trying everything to these clever strategies.
Dynamic programming, binary search.
Yes.
It's super cool.
Absolutely.
Okay, so last time we left off talking about representing these algorithms.
Uh-huh.
Can we, like, actually see how that works? With pseudocode or something?
Absolutely. Pseudocode, it's like, not real code exactly.
Right.
But it helps us, like, lay out the logic.
Okay.
Using, plain language and some code-like stuff.
So it's like a bridge between the idea and the actual code.
Exactly. Makes it clearer.
Awesome. So where do we start?
Let's do that binary search one with its helper function.
Minimum subarrays required.
Yeah, that's the one. So imagine we have a function, call it minimum subarrays required.
Yeah.
It takes two inputs,
Okay.
our array of tasks. Well, let's call it tasks.
Okay.
Tasks. And that guessed sum, we called it max sum allowed.
Right. Max sum allowed, like, can we split it without exceeding this?
Exactly. So inside this function,
Yeah.
we need a couple of variables.
Okay.
First, subarray count started at 1 because we always have at least one subarray. And then current sum, that's going to keep track of the sum in our current subarray, starts at 0.
Okay, so we're, like, starting fresh with one subarray and no sum yet.
Right. Now, we go through each task in our tasks array.
Okay.
For each one, we add its size to our current sum.
So we're adding tasks to the subarray, but only if we're still under that max sum allowed limit.
Exactly. Now, if current sum goes over max sum allowed,
Uh-oh. Gotta start a new subarray.
yep, we bump up subarray count by 1
Okay.
and reset current sum to the current task's size.
So it's like we hit the limit, new subarray, start counting from the current task.
You got it. We do this for all the tasks.
And at the end.
We return the subarray count.
So that tells us how many subarrays we needed to make it work.
Exactly. Whether our guessed sum was doable or not.
Okay, that makes sense.
Right.
Now, how does this all fit back into the main binary search part?
Remember our main function, let's call it calculate minimum largest sum,
Okay.
takes our tasks array, and k, the number of subarrays we want.
Right. Calculate minimum largest sum, our starting point.
Inside this function,
Uh-huh.
we first got to find our low and high values for the search range.
Right, a Goldilocks zone. Not too big, not too small.
Exactly. Low is the biggest element in tasks.
Okay.
High is the total sum of all elements.
Gotcha. So those are our boundaries.
Now, the binary search loop,
Okay.
it keeps going as long as low is less than or equal to high.
Right.
Each time, we calculate the middle value, call it mid.
I guess.
Yep, our potential minimum largest sum.
Okay.
Then, we use our minimum super is required function,
Uh-huh.
give it tasks and mid.
Checking if it works.
Exactly. If the count it returns is less than or equal to k.
We're good. It's feasible.
Yep. Could even be smaller, though, so we update high to be mid 1.
Okay, focusing on the lower half.
Right. If it's not feasible, gotta go higher, so low becomes mid plus 1.
Upper half. We could keep going back and forth.
Exactly. Until low is greater than high.
And then, boom, we've got our answer.
Low will be our optimal minimum largest sum.
Wow, it's like a super smart narrowing down process.
Binary search is all about efficiency.
Way better than just trying every combination.
Definitely. But, each algorithm has its place.
Right, right.
Dynamic programming, it can be easier to grasp sometimes.
Yeah.
And that bottom-up way can be good for saving memory.
So it's about knowing your tools.
Exactly.
This has been an amazing deep dive. We've learned so much.
It's been fun.
From brute force to dynamic programming to binary search.
Quite a journey.
And thanks again to our listener from AI.Code.Cast for the great question.
Yeah. Great problem.
This is exactly why we do these deep dives,
Totally.
taking these complex ideas and breaking them down into something we can all understand.
Absolutely.
So to all our listeners out there, keep those coding challenges coming.
Yeah, we love them.
And until next time, happy coding.
Happy coding.